Searching the internet for LocoNet and DCC interfaces for microcontrollers and computers produces a good number of results. But are they suitable to feed the signals to the IoTT stick? In this video I am going to find out, and I show you the schematics of the interfaces I finally decided to use with the IoTT stick. So, welcome to the Internet of Toy Trains. I am Hans Tanner. I noticed that the IoTT channel made it to 750 subscribers this week, so a special welcome goes out today to all recent subscribers. Thank you for coming on board, and if you are new here and like what you see, please consider subscribing and click that bell icon so that you have a premium seat every time new videos become available. Doing a Google search for LocoNet interfaces produces several different schematics, which at their very core are all pretty much the same. LocoNet is basically a single wire bus with the voltage on that wire above 4 volts when no communication takes place. All that's therefore needed is a level changer from the LocoNet voltage to the receive pin of the microcontroller, plus a transistor that allows you to drive the LocoNet wire low when you want to transmit. That's it. And as I go quickly over several circuits I found on the internet, I have marked the relevant areas of each in blue for the receiving and yellow for the transmitting part. The most prominent design is probably this one here from John Blotcher, which is shown on several web pages. And I like it because it has just the bare minimum of what is needed to make a LocoNet interface work. The LocoNet signal is fed into a voltage divider consisting of R23 and R24, which brings the nominal LocoNet voltage of 12 volts down to about 9 volts. The total resistance of the two resistors is about 200 kilo ohms, which easily fits the minimum input impedance of 47 kilo ohm required by the LocoNet standard. The reduced voltage is then fed into the LM311 comparator in the blue circle. The second input of the comparator is supplied with a constant voltage of about 3.3 volts from the voltage divider formed by R21 and R22. The output of the comparator is a binary signal of 0 or 5 volts depending on the state of the LocoNet input. If LocoNet is high, the RX output is high, and vice versa. The RX output is then connected to the input capture pin of the microcontroller. The transmit signal TX comes from the output pin of the microcontroller. If it goes high, the transistor Q2 in the yellow circle is activated and pulls down the LocoNet data signal to ground. So, to just receive data, the transmit pin is low and the data can be received on the RX input pin. To transmit data can be sent via transmit pin, and while going out via LocoNet data, it is also mirrored back to the RX pin, which allows for checking for communication errors, something every LocoNet device is required to do while transmitting. The oldest design drawing I found is from 2002 on the Fremo webpage. Stefan Hawk came up with this PC interface, basically a replacement for the Digitrax MS100. It interfaces LocoNet to a standard RS-232 serial port of a PC. In addition to the receiving and transmitting elements, it features full opto-isolation of LocoNet from the PC circuitry, so it had a clear advantage over the MS100. Another interesting feature of this interface is shown on the second page of the schematics. There is a 15 mA current source which can be activated so the interface can act as LocoNet terminator, in case you want to build a local LocoNet without Digitrax command station. The next 3 designs are all identical to John Blotcher's circuitry. In fact, the first one is from John's webpage and just shows a version he used to make a LocoNet shield for Arduino. The only difference I can see is an additional resistor R8 of 47 ohms in the LocoNet activation path. I have no idea though what that would be good for. The next 2 are identical. I just show them to document how widespread this design is. If you want to study them in detail, you find the web links in the description below. The next level would then be Dick Bronson's Loco buffer. Again, it has the same basic circuits for receiving and transmitting. It also has opto-isolation like the Fremo device. And in addition, it has its own microcontroller which allows for some buffering of the messages, hence the name Loco buffer. The bare minimum solution is shown in the next slide, a version that is only using a voltage divider without comparator. As the disclaimer on top of the page says, it is not a very robust design and I would discourage from using it. I am showing it here because it is so simple that it is very easy to explain what I see as the main problem with the de facto standard way to interface LocoNet to a microcontroller. As mentioned, LocoNet is high when it is quiet, so the ICP pin is high too. When data is received, the ICP switches between high and low as the bits are received. The transmit pin thereby is constantly low, so the data flow is not disturbed. The ICP pin is non-inverted while the output pin is inverted. This becomes even more clear when in transmit mode. To send a start bit, the output pin goes high. This drives LocoNet low and the ICP pin therefore goes low as well. Again, ICP is non-inverted and the output pin is inverted. Why could this be a problem? Well, it is no problem at all as long as the difference is handled in software. And this is what the LocoNet library that you can download from the Arduino IDE does. However, if you want to use a hardware serial port, you run into a problem as the hardware serial driver cannot be configured for RX and TX using different logic. It can be configured for inverted, but that would then be for both pins. Now again, this is not a problem when using a simple Arduino, because there is no such thing as an additional hardware port you could use. For the ESP32 as used in the IoTT stick, that's a different thing. As I have explained in videos number 27 and in more detail in video number 28, in order to make LocoNet work 100% reliably on an ESP32 with active Wi-Fi, it is best to use a hardware serial port for receiving and then software for transmitting. Only this way it is guaranteed that no incoming data can be missed, while collision detection can be done on bit level. And for that, using pins with two different logic levels is not very convenient, to say the least. So for that reason I changed the design so that both pins transmit and receive use inverted logic. I did that by swapping the comparator inputs as you see in the resulting circuitry. The resulting signal is then fed to pin 1 of the Grove port connector. Grove is a standardized interface to facilitate building quick setups using a microcontroller and some sensors without soldering. If you want to know more about it, there is a link in the description below. Since the ESP32 pins use 3.3 volt logic, I added a Zener diode D4 to limit the voltage. When the interface is used with a standard Arduino using 5 volt logic, the 0 ohm resistor R7 should be removed so the input pin gets 5 volts. The output is standard, just an output line from pin 2 of the Grove connector activating a transistor which pulls the LocoNet line low. This output works with both 3.3 and 5 volt logic, no worries. The next element I put in is a 15 mA current source so the interface can act as a LocoNet termination. To activate it is enough to connect a 12 volt power supply and that's it. What about opto-isolation of the data lines? Well, I considered it for a while but then decided against it. I agree that isolated signals are preferable when connecting to a computer. However, in this case we are just connecting to a microcontroller which ideally is supplied from a potential-free power supply such as a phone charger. Furthermore, if the wiring is done correctly, there should be no potential difference between LocoNet ground and ground provided by a computer-connected USB-C cable, so the risk of a ground loop is minimal. So I decided to move electrically isolated communication lines to the other side of the IoTT stick, to the head that makes the data interface to a computer's USB port. However, On the PC board I added resistor R9, another 0 ohm resistor, which is the bridge between LocoNet ground and ground of the IoTT stick. If there is ever a ground loop problem, the 0 ohm resistor can be replaced by a 10 ohmish one, which then at least provides some protection. This is, by the way, if my memory serves me right, exactly the approach that Digitrax used for the original MS100 interface back in 1994 or so. From this schematic I generated a PCB along with parts list and placing information for a pick and place robot. I also designed an enclosure along with an STL file for a 3D printer. If you want to build the interface for your own use, you can download everything from my GitHub page linked below. Alternatively, you can order a fully tested breakout board from Amazon. I am currently in the process of setting up my Amazon page, so it should become available in the next 2 weeks or so. Also from my GitHub page you can download LocoNet libraries for the ESP32 and the Arduino that supports inverted signals on both transmit and receive. I also asked Alex Shepard, who is the maintainer of the LocoNet library that can be downloaded from within the Arduino IDE, to add the configuration option to make the receiving pin logic changeable. So it's in the makings, but might take a while. In the meantime, you can download and install it from my GitHub page. Now, if you are already bored with all this engineering stuff so far, it's probably time for you to say goodbye, because with the DCC interface it's only getting worse. Building a DCC interface is not complicated as long as it is for a decoder that is only connected to DCC and takes energy and information from the DCC signal. I have done that in video number 16 for the servo decoder using this simple circuit. And if this looks too complicated, you can even make it simpler. So here is the minimum circuitry needed for a DCC interface for a decoder. Using this for the IoTT stick, however, is not a good idea, because there will be a potential difference between the ground from the rectified DCC signal and computer ground. So there will be some destructive ground loops. Therefore, in this situation, optical isolation is needed between the DCC signal and the IoTT stick. My starting point for a fully isolated DCC interface again was what's already available. Like in the case of the LocoNet interface, there is some sort of a reference design that is used in several published interface versions. Here it is as published by OpenDCC in Germany. And exactly the same in a design from Iowa Scaled Engineering. With the exception of a different value in the series resistor R1, they are identical, and there are many others out there. So my first step was to build this circuit on a breadboard and then study the signals it produces. Of course, for the IoTT stick, one of my design goals was to build an interface that works for all standard voltages from N to G scale and with some reserve. So I tested the circuitry with all the power settings of my command station. The first measuring point was the DCC signal output, so the output of the optocoupler. I tested it with open output, meaning just a 10K pull-up resistor to 5 volts, and then with the output connected to an Arduino I/O pin. As you can see, the signal has a significant asymmetry. The negative flange is nice and clean, but the positive flange is slow and takes quite long to recover to the 5 volt level. In fact, when driving to the I/O pin of the Nano, it would not even reach 5 volts before it is driven low again. When I changed the voltage to 3.3 volt, the signal characteristics was basically the same. Even slower rise and a steep fall. It seems the pull-up resistor is simply too high and therefore not capable to drive up the signal against the capacity presented by the opto output, wiring and I/O pin. This may or may not be a problem for the decoding software, depending on what flange is used to trigger the interrupt. But if the rising flange is used, it is possible that some timing problems may occur because it is rising relatively slow. To test, I changed the 10K pull-up resistor to a 4700 ohm and repeated the measurement. The signal quality improved significantly, resulting in a much more symmetric output for both voltage levels 5 and 3.3 volts. With that in mind, I was confident that I could make the output side work nicely, so I turned my focus to the DCC input side. The design is very simple, basically just the LED of the optocoupler, an anti-parallel diode to protect the opto from the reverse voltage of the DC pulse, and a resistor to limit the current. To make it work, the forward current in the opto must be at least 5 mA and must not exceed 25 mA. The forward voltage is around 1.4 volts, so the DCC voltage is basically reduced by the serial resistor and the current changes with the DCC voltage. Also, there is a current flow in the series resistor for both polarities of the DCC signal. It is even higher when the polarity is reverse because the protection diode forward voltage is only around 0.8 volts. So the interesting question was, how is the current through the optocoupler going to change with changes in the DCC voltage, and what is the power dissipation in each case for the different scale voltages? To find out, I measured the voltage difference over the 1K resistor and calculated the resulting current and power dissipation. Here are the results. For N scale, the current is 9.5 mA, which results in a power dissipation of 90 mW. For HO scale, the current is 12 mA and about 144 mW is changed into heat. And for G scale, the current is 18 mA, resulting in 324 mW contribution to global warming. This was actually enough to hurt my finger when touching the resistor. So, if I wanted my breakout board to be usable for all input voltages, this simple front end is not an ideal solution. Maybe I have a tendency for over-engineering, but at the end I decided to use a voltage regulator to bring any input voltage down to 5 volts and drive the optocoupler always under the same conditions, independent of the scale-related voltage. Here is my circuit design. The DCC signal is rectified and fed into a voltage regulator, which brings it down to 5 volts, independent of the DCC voltage. The regulated voltage is the supply voltage for the DCC side of the circuit. The DCC signal is also used to drive transistor Q2, which drives the optocoupler LED. The LED forward current is around 15 mA, which is exactly the manufacturer recommended value. The overall power consumption is also reduced as there is only current flowing half of the time, which helps the voltage regulator to stay below 40 degrees Celsius, even when using G-scale voltage. On the Arduino side, I am again using a 3.3 volt Zener diode to limit the voltage for the ESP32 input lines. To use the board for 5 volt inputs, the 0 ohm resistor R6 can be removed. The output signal from the ESP32 can be used to generate a programming acknowledge pulse. It drives the input of the second optocoupler, which then activates a current source that creates the additional current consumption on the DCC lines. Note that the current source is located before the voltage regulator and also separated from it by the diode D3. This is to make sure that any additional current comes straight from the DCC lines and cannot be supplied by capacitor C2. Looking at the resulting signal, this is what I got. The DCC signal going to the Arduino looks really nice. It is almost symmetrical with steep rising and falling flanges. Second, I did a quick test program to generate acknowledge pulses and measured it on the DCC side by measuring the voltage on R11. The resulting pulse comes through and generates an additional current of about 60 mA, which is exactly what the DCC standard is asking for. The final thing I wanted to know is the signal latency caused by the optocoupler. This is important when using the breakout board to drive, for example, a booster. The DCC signal out of the booster should not have too much delay compared to the original signal, or short circuits may result when a wheel crosses the gap between booster districts. So I compared DCC input with optocoupler output, and the result was not good. Driving down the signal line was fast, but when going up, there was a 4 microsecond latency. That's of course not acceptable. Looking over the schematic again, I noticed that I forgot to add a discharge resistor to the transistor space, so it had a hysteresis. I added a 4.7 kilo ohm resistor, which is easy to correct on the PC board, and here we go. All the latency gone. The signal following the DCC input within nanoseconds. As with the LocoNet interface, I generated a PCB from this schematic along with part list and pick and place information. I also did an enclosure along with an STL file for a 3D printer. If you want to build the interface for your own use, you can download everything from my GitHub page linked below. And like the LocoNet board, also the DCC breakout board will soon be available on Amazon. To drive the board from Arduino, you can use the NMRA DCC library that can be downloaded from within the Arduino IDE. It works for all platforms and allows you to decode the incoming DCC commands in real time. I also started to set up my IoTT.org webpage, where I will publish more information and documentation, software updates and links to the relevant GitHub repositories and Amazon pages. So that might become a good landing page for everything related to the IoTT stick. And that's it for this video. I hope this information was useful or at least interesting for you. If so, please click the like button below. Doing so does not only help to boost my ego, but also helps to promote this video and the IoTT channel in general, because the YouTube algorithm likes the likes. Thanks for watching and see you next time.